Here's the definition that helped us solve the fire engine problem. For any vector b and another vector a, we defined the projection of b along a, b parallel, and the projection of b orthogonal to a, b perp, so that b is the sum of b parallel and b perpendicular, where b parallel is a scalar multiple of a, and b perpendicular is orthogonal to a. We use a generalization of this definition to address the least squares problem. For a vector b and now a vector space, big V, we define the projection of b onto big V, written b parallel, and the projection of b orthogonal to big V, written b perpendicular, so that b is the sum of b parallel and b perpendicular, and b parallel to V is a vector in the vector space V, and b perpendicular to V is orthogonal to every vector in the vector space big V. So again, we're decomposing B as a sum of two parts, the parallel part and the perpendicular part. Now recall that the fire engine lemma gave us a way to identify the point in span of A closest to B. It was the projection of B parallel to A, and the distance was the norm of the projection of B perpendicular to A. We generalize that as follows. The point in a vector space, big V, that's closest to the vector B is B parallel, and the distance is the norm of B perpendicular. Now, suppose big V is specified by generators, V1 through Vn. Then our goal is an algorithm for computing B perpendicular from the inputs, the vector B, and the generators, V1 through Vn. The output should be the projection of B orthogonal to the vector space big V, which is the span of V1 through Vn. Now, we already know how to solve this when we only have one generator. We use project orthogonal 1. Given a vector B and a single vector V, the solution is to take B and subtract out from it the projection of B along the vector V. So let's take this algorithm and try to generalize it to higher dimensions. So here's the algorithm we have, and here's the natural generalization to higher dimension. The input is a vector B and a list of vectors, and the algorithm goes through the list of vectors and for each one subtracts out from B the projection along that vector, and then returns the result. Well, what do people think about this algorithm? It's short, elegant, and flawed. Beautiful if only it worked. A tragic failure. So let's see this algorithm in action. Let's say we're given the vector B, which is 1, 1, and our V list consists of 1, 0, and root 2 over 2, root 2 over 2. So the red is the vector B. The first vector in V list is this one, 1, 0, and the second one is this one, root 2 over 2, root 2 over 2. Let's see what the algorithm does to B. We'll let bi denote the value of the variable b after I iterations. So initially, at input, the value of b is b0. In one iteration, the algorithm derives b1 by taking b0 and subtracting from it the projection of b0 along the first vector of v-list. Okay, so the first vector of v-list is 1, 0. So we're subtracting the projection of 1, 1 along 1, 0. Well, here's the projection. It's just 1, 0 itself. So when we subtract that from b0, we just get 0, 1. So here's b1, the value of the variable b after one iteration of our proposed algorithm. Next, we have to derive b2. And b2 is derived by taking b1 and subtracting from it the projection of b1 along the second vector in v-list, root 2 over 2, root 2 over 2. So here's the projection of B1 along the second vector in V list. And the result of subtracting that, B1 minus 1/2, 1/2, is here. All right. Well, this is a failure. Of course, the resulting vector B2 is orthogonal to the second vector in V list because we just subtracted off the projection along that second vector. But doing so destroyed the orthogonality between B and the first vector in V list. So we established that in the first iteration, and then we destroyed it in the second iteration. The result is not orthogonal to the first vector in V list. So this algorithm, beautiful as it is, doesn't get us the right answer. Well, maybe there's a way to fix it. Maybe if we instead find the projection of B along each of the vectors in V list and then subtract off all those projections. Here's the algorithm. I call it classical project orthogonal. It initializes the output to the all zeros vector and then runs through each of the vectors in V list, finding the projection of B along that vector and adding up all those projections. At the end, it returns the result of subtracting the sum of those projections from B. Does this algorithm work? No, this gives us the wrong answer as well. In fact, if you run it on these inputs, the output vector is not orthogonal to either of the two vectors in V list. So this fails spectacularly. But here's an example where it works. You take these two vectors, V1 and V2. These vectors are orthogonal. So these two vectors represented here, and the vector B represented here. In the first iteration, the algorithm takes the initial value of B and subtracts off the projection of that vector along V1, getting B1. So here it is. So it gets this vector. In the second iteration, it takes B1, the value after the first iteration, and subtracts off the projection of that vector along V2. And here's the vector, and here's the result. This vector is orthogonal to V1 and V2. Was it a coincidence? Let's do the math under the assumption that V1 and V2 are orthogonal. Remember, Bi is the value of the variable B after I iterations. In the first iteration, we obtained B1 by subtracting from B0 the projection of B0 along V1. So that gives you a vector B1 that's orthogonal to V1, the first vector in V list. So the inner product is 0. In the second iteration, the algorithm derives B2 by taking B1 and subtracting off the projection along V2, giving a vector B2 that is orthogonal to V2. Its inner product with V2 is 0. But what about the inner product of B2 with V1? Have we lost orthogonality? Well, let's see. The inner product of V1 with B2 is the inner product of V1 with B1 minus sigma V2, the projection of B1 along V2, the thing we subtracted off in the second iteration. Using an algebraic rule of inner product, we can break this up as the inner product of V1 with B1 minus the inner product of V1 with sigma times V2. We can factor out the sigma to get the inner product of V1 with B1 minus sigma times the inner product of V1 with V2. Now, the inner product of V1 with B1 is 0 because B1 results from subtracting off the projection along V1. So this inner product is 0. This inner product is also 0 because we assumed that V1 and V2 were orthogonal. So we indeed get 0 when we take the inner product of V1 with B2. Thus, the result is orthogonal to both vectors in VList. The solution then for project orthogonal is not to throw away the procedure, it's to change the spec. So we'll now require that the input list VList consists of mutually orthogonal vectors. That is, all the vectors, every vector on VList is orthogonal to every other vector on VList. So the spec for the procedure is it's given a vector B and a list VList of mutually orthogonal vectors. And it's required to output the projection of B orthogonal to all the vectors in VList. To show that this procedure satisfies its spec, we'll define a loop invariant, and we'll prove it's correct. As before, let bi be the value of the variable b after I iterations. The loop invariant requires that bi is the projection of b orthogonal to the first I vectors in VList. That means bi is orthogonal to those first I vectors, and b minus bi is in the span of those first I vectors. We'll prove this invariant holds by induction. And the case I equals 0 is very easy. B0 is certainly orthogonal to the first 0 vectors. Every vector is orthogonal to an empty set of vectors. And b minus b0 is in the span of the first 0 vectors because b minus b0 is the 0 vector. So now we want to prove the induction step. So here's the invariant that we're trying to show. That bi is the projection of b orthogonal to the first I vectors in VList. And what that means is that bi is orthogonal to those first I vectors, and b minus bi is in the span of those first I vectors. Here's the procedure. And let's assume that the invariant holds after k minus 1 iterations, and we'll show that it also holds after k iterations. In the kth iteration, the algorithm computes bk, which is bk minus 1 minus the projection of bk minus 1 along the vector vk. So that projection is, of course, a multiple of vk. Now, by the inductive hypothesis, we assumed that bk minus 1 satisfied the invariant. That is, bk minus 1 is the projection of b orthogonal to the first k minus 1 vectors. What we have to prove is that bk, the next iterate, is orthogonal to the first k vectors, and b minus bk is in the span of those first k vectors. We computed bk from bk minus 1 by subtracting off the appropriate multiple of vk, the kth vector in VList. The multiplier was chosen to ensure that bk was orthogonal to vk. But what about all the vectors in VList that occur before vk? We have to show that bk is also orthogonal to them, to vj for j equals 1, 2, 3, and up to k minus 1. Let's take the inner product. The inner product of bk with vj, well, we know what bk is. It's bk minus 1 minus sigma k vk, so we plug that in. The inner product of bk minus 1 minus sigma k vk with vj. And using some algebraic properties of inner product, we can rewrite this as the inner product of bk minus 1 with vj minus sigma k times the inner product of vk with vj. Now, the inner product of bk minus 1 with vj is 0, because by the inductive hypothesis, bk minus 1 is orthogonal to all the vectors in VList up to vk minus 1. This inner product is also 0 because we've assumed that the vectors in VList are all mutually orthogonal. So the result is that the inner product is 0. So that shows that bk is orthogonal to the vectors v1 through vk. But we also have to show that b minus bk lies in the span of the first k vectors of V list? Well, b minus bk is b minus bk minus 1 minus sigma k vk. We can rewrite that as b minus bk minus 1 plus this multiple sigma k of vk. Well, this first quantity is a vector in the span of the first k minus 1 vectors in V list by the inductive hypothesis. The second quantity is just a multiple of vk. Since we're adding something that's in the span of v1 through vk minus 1 and a multiple of vk, the result is a vector in the span of v1 through vk. So we've proved the second property. And that completes the proof. All right, we've gotten through that proof. We've shown that this procedure has the following property, that given a vector b and a V list consisting of vectors v1 through vn, it outputs the vector b perpendicular such that b equals b parallel plus b perpendicular, where b parallel lies in the span of those vectors in V list, and b perpendicular is orthogonal to each of them. Now we're going to work with the code a little bit, and for that reason I want to restate the correctness using zero-based addressing. So the list consists of the vectors v0 through vn, and b parallel is in the span of the vectors v0 through vn, and b perpendicular is orthogonal to v0 through vn. We're going to need a procedure that gives us a little bit more information. Since b parallel, which is b minus b perpendicular, is in the span of v0 through vn, there exist coefficients alpha 0 through alpha n such that b minus b perpendicular equals the corresponding linear combination, alpha 0 times v0 and so on. We can move b perpendicular to the other side, so we get this. B equals this linear combination plus 1 times the vector b perpendicular. And we can write that in matrix form as b equals the matrix whose columns are v0 through vn together with b perpendicular times this column vector consisting of alpha 0 through alpha n followed by the 1, the coefficient of b perpendicular. So we're going to augment the procedure project orthogonal to actually output this vector of coefficients as well as b perpendicular. And for technical reasons, we're going to represent that not as a vec, but as a dictionary. So here's the defining equation. The procedure has to create this dictionary that has one entry for each of the vectors in V list, together with one additional entry, the 1, that's the coefficient of b perpendicular. So we initialize the dictionary with that 1 element. We're going to derive the code from 2 previous procedures, project along and project orthogonal. And here's the augmented procedure. It initializes the dictionary. In each iteration, it pulls out the vector, computes the scalar multiple sigma, then populates the dictionary with that value of sigma and updates the value of b. At the end, it returns the value of the variable b, which is b perpendicular, and the dictionary of these alpha values together with the 1. Later on, we'll use this procedure.